Hello, so I'd like to introduce the concept of the model of Lambda-Calculus and how it's a great improvement with respect to functions and in some sense a superior model of computation. So we've looked at recursive functions, and I need something to write. We've looked at recursive functions and so we've defined it, with certain, say, the add function with the recursive schema. So add x0 equals f of x, and it's always the same definition, schema of definition. X, h of x, and f and g are going to take certain value. In this case, we say where f equals p11 and g equals s composed with pi 2, 3. Okay, so that's the definition of addition, and we saw that we can compute pretty much any arithmetic function that way. Okay, now there are traditionally there have been a lot of issues and essays to point out to a lot of ambiguity and implicit assumptions here in the way functions work. There are several implicit assumptions. For instance, here we clearly don't put x and Sn at the same level. We assume that x is a given number, say 1 or 0 or any number, and S of n, we assume this is given. Sorry, but that we assume that somehow this is given and that somehow this is the variable, right? You're going to add 0 to 1 or 2 or 3, and depending on how long and how big this number is, you're going to do a certain number of computation here, of recursion, right? So there is an assumption that these two are not exactly on the same level, right? And that's part of the issue, is that there is no way to see that. Of course, the order doesn't matter, right? You could have Sn, x or x, Sn, and for any function that has multiple variables like that, the order really doesn't matter and doesn't tell you anything about the order of substitution of the variables. So let me take another example maybe that will be a little bit more illustrative of what I'm trying to say. If you have a cost function for a certain service you're going to buy, like fixing a car, for instance, right? So your cost function is going to depend on hours of the cost of labor and the cost of labor, so that's P for the price of labor, and the number of hours, right? And you're going to have maybe uncompressible, like minimum cost, maybe the cost for the pieces or the parts, sorry, or something like that. So you're going to have, say, a minimum cost of 10 plus the hourly rate times the number of hours, right? Okay, so that's a perfectly fine function. It's perfectly well defined, as a function. But now, clearly here there is the assumption that if you are in the process of determining the cost, you already have a price. So the price is both a variable, but it's also a given. It's also more of a parameter than a variable. So, so in some sense, P and H are not at the same level, right? What's going to vary, and that the thing that the true unknown in this equation is more H. The price is somewhere in the quote. I mean, the quote. It's somewhere. If you have the quote, maybe you have a number of hours, but we assume we don't have it yet. It's somewhere on the website of the car mechanic or whatever. It's somewhere displayed. Anywhere. So the price and the hour are not the same level. In some sense, you can think of of the price as being one of those constants that you put as maybe a global variable or a parameter at the beginning of your program in C or Java, you know, like max size, for instance, for the maximum size of an array or something like that. Well, the max size is a variable and it is not. It's more of a parameter. And it's not the same level as the x, I, j, n variable that you're going to use in your program that are going to depend on something that the user input or something like that. So there is variable and variable. Function doesn't make that explicit at all. There is no meaning in the order, right? I mean, this, what's the difference between this and this? None. And that's a little bit of a problem actually, because the form is different. And if you have a different form, you should have a different meaning also. That's kind of the idea also behind Lambda-Calculus. So, so here we have a little bit of implicit assumptions that are problematic. And really what Lambda-Calculus is trying to do is to make all of that explicit. So the first implicit assumption is I would call it the order of substitution. You're going to substitute here in a certain order. So for instance, as we said, the price might be the first thing you're going to know, right? So you're going to have something like, you know, C, and you know that the price is 20, say. C20H equals 10 plus 20 times H, right? And but this is kind of an odd, so what is that? Is that a new function? And it looks like it's a new function because it's not defined exactly, but we just replaced the 20. It's not really a proper function. A proper function only has variables in the, so I need to redefine it. So let's call it maybe C20 be such that C20 of H equals C20 of H, right? Equals 10 plus 20 times H. So you have to redefine a new variable, and maybe you could call it, you know, instead of C20, you could call it just G, I don't know. But you're going to have to redefine it, redefine a new variable because you have a new equation, because you did a substitution. So here there is the assumption that you're going to replace the price first because it's more of a parameter, and then the hours, but there is no way to see that in the function, right? And it's kind of the same thing I was talking about here. In some sense, there is this assumption that this is a given number, and this is the one that actually varies, and that's going to make the pattern vary of pattern of recursion. Have more or less nested recursion, but this is implicit. Okay, so that's the first implicit assumption. There's another one that is, and again with this implicit assumption, there is also the ambiguity that comes with, is this different from this? How is this different from this? And now that we have applied, we need to redefine a new function. Okay. There's another implicit assumption, which is there is clearly an order here, right? This is more on the left side of the equal, what we define, and on the right side is the definition / computation, how you compute it, right? But equal signs in mathematics are agnostic with respect to order. So there is no reason why we could not rewrite this as f of x equals add x0 and g of x, here I should have put add, sorry about that. Add xn n equals add x Sn. But all of a sudden that doesn't make as much sense, right? If you read that in English, if you want, if you read that in the order from left to right, it is not very meaningful. It's actually very confusing in some sense. So that's the other implicit assumption, is that there is an order here in the equal sign, where on the left you have what to compute, and on the right is how to compute it. In the realm of function, there is no way to encompass that idea of process or computation, right? Ultimately, add 2, 3 equal 5 doesn't have any order here. But I clearly know that this comes after this. This is a question, this is the answer. So the problem is that from a purely formal, like recursive function perspective, there is none of that actually has an order. These two live together, the add 2, 3, and the 5, as equal at the same level. They live also as equal. They are equal in the order of computation. There is one that comes before the other. From a purely formal perspective. Now I know if I compute it, I know they're going to be in order, because in my mind I'm doing that process. So there are two things I'm doing in my mind that is not actually expressed here formally. First thing, I'm actually ordering those in terms of which one do I substitute first, like I did here. That's first implicit assumption. Second thing is the order of computation. That's the second thing that I am actually processing differently than what is written. What is written is everything equal same level. But what I do is, well, I first take 2 and 3 and then I get 5, not the other way around. Right? So from a pure function perspective, a function can be seen as an ordered pair, right? So in some sense, the function add is defined as a set of ordered pairs among which I'm going to have 2, 3 paired with 5, right? Again, both at the same level, right? There's not this notion of computation. Lambda-Calculus makes explicit these two implicit assumptions. Here is how it does it. Well, let me write this as a lambda term. So it's going to be lambda p h 10 plus p times h. And so here is contained much more information in here in some sense. Why? First, it says you're going to replace p first and then h. It gives you an order of substitution. First replace p and then h. So now if I apply this, that's my program. I don't want to call it a function because I don't think it's a function in this sense. It's my lambda term, my lambda abstraction, which we can think of as a program. And my program is going to first process p because it's written in the definition here. So there's not this idea that I could intervene, I can, if I change these two, it's a different lambda expression. It's a different lambda term. Unlike here, doesn't change, not different. So another thing we could notice is that if now I apply this to 20, which means I'm just going to be able, if I do the beta reduction, and we'll go back to that, that means we're going to replace all the instances of p by 20, I get a new lambda term. That is also a lambda term. Well, here I didn't know really when I replaced by 20, is that really a function? Well, I need to redefine it. I need to define a new function g. Now let's say, okay, g of h equals 10 plus 20 times h. Now I don't need to redefine anything. This is g. Just by applying a lambda term to 20, by my initial program, lambda term to 20, lambda abstraction to 20, I generate automatically a new lambda term. It's part of the definition of the lambda abstraction. I can apply and keep putting some variables or constants here, and I generate new lambda terms without having to redefine with the equal sign. Right? Here I need to redefine, recreate a definition. Right? So in some sense, you can think of it as multiple assignments you have to do in a procedural language. This is more of a functional take where I can just apply functions to elements and I get new functions. So here I get a new lambda term that defines exactly what I want, is that when I have the price, and if I apply that to a number of hours, I'm going to get the actual cost. Okay? Now, there is no more ambiguity with respect to the order of substitution. What about the order of computation? Well, same thing here. There is no equal sign in Lambda-Calculus. You will notice, you can look, Lambda-Calculus never have any equal sign. Equal doesn't mean anything. Well, you can define equality in terms of Lambda-Calculus, which shows that Lambda-Calculus in some sense lives over all of that, right? You cannot define Lambda-Calculus within the formal framework of functions, but you can do the other way around. You can define all of that with Lambda-Calculus. So Lambda-Calculus in some sense lives at a higher level of abstraction and englobes more possibility, more expressivity than recursive function. Now there is the order of computation in Lambda-Calculus because I can now beta reduce this, right, through what I call beta reduction with this sign into, sorry, it's going to be a little bit below here. So now I substitute P for 20, so I'm getting lambda H 10 plus 20 times H. Okay, that's my new expression. I just beta reduced. And I can now apply that, if I want, to a certain price, say 5, right? And I do the substitution of the number of hours to get 10 plus 20 times 5, and that's it. That's the normal form. If I want to compute it, that's called an evaluation. It's not a beta reduction anymore. It's an evaluation, and I can evaluate that to 110, right? So I get my price. But what is important is that there is clearly here an order of computation where here I could not really make explicit which one comes first. Is it this one or this one? I know it's this one, and this one comes second, but it's not expressed formally. Here it's clearly expressed through the concept of beta reduction. This is my program before application, and I can actually even express my 1 and 10. I mean, this expression even more abstractly by just here adding a 10, right? So if I do lambda ph 10 plus p times h 20 10, this is my full this is the maximum knowledge I put there, right? I'm saying apply my program to 20 and then to 10. And so, and same thing here. This is also a lambda term. So I don't need any redefinition. I can just apply, add elements, add variables to which my lambda abstraction is applied. And what is really interesting is that indeed I can see the order of computation, right? This comes before this, right? There is my program not beta reduced, unreduced or untouched if you want. And then this is the state after reduction. There is a before and after. And as you notice, it's not by chance that we have here inequality sign, right? Inequality shows clearly there is an order. This one, it's not that this one is greater than this one, it's that this one becomes before this one. So there is clearly here the notion of computation that is not encompassed in the notion of function. So there is an order. In this order we beta reduce, in this order we beta expand, okay? And so, so Lambda-Calculus solves these two ambiguities or implicit assumptions by really making them explicit in the formalism, by clearly stating what is the order of substitution and showing the order of computation, okay? So in this sense, Lambda-Calculus is closer to a computational model as it should be than recursive function, just like the Turing machine, which has also clearly an order, right? Configuration 1 comes before configuration 2, and there is no way to miss that. It's actually implicit. I mean, it's actually explicit. Sorry, in the formalism. Okay, so I just wanted you to see that. Now, if we try to compare with Turing machine, we can also see that Lambda-Calculus is somehow a higher level of formalism because it doesn't depend on states or an alphabet or things like that. It defines at a very, very abstract level some entities like numbers and operations and things like that. So we can, it's a very expressive formalism. We can describe a lot of things within the framework of Lambda-Calculus, which is not necessarily the case for the Turing machine. Okay, I hope this was helpful to understand the motivation behind Lambda-Calculus and why Alonzo Church came up with it.